Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode 21, where today we're going to be talking about Astronomy Part 3, per request.
Per request, this is the third installment, and before we actually get into the content of this episode, we're actually going to be going through our comments that we've been getting on YouTube, because we actually haven't been looking at our comments, but it's not our fault. We just haven't been getting the notifications. But yesterday, I was on the email for our YouTube account, and I saw all the comments we got. So today, we're going to make sure you guys don't go unnoticed. We're going to answer your comments live on the air, and then we're going to get onto the podcast. So The first comment we got, this was 2 months ago. Nati Base, this is actually my friend. I know him from high school. He says, "Geez, very thought-provoking. We appreciate it." We appreciate the encouragement there. And then Jeff Liu says, "Great content, guys."
That's my boy Jeff Liu. He commented, "Great content, guys. Keep up the good work. Really appreciate it."
Yeah.
Yep.
Thank you very much.
Then Rudra Singh is actually he was actually in my high school, and he was a good friend of mine. He says, "Keep up the good work. I'm only in middle school." Wait, what? Oh, then I'm talking about a different Rudra Singh. Never mind. Never mind. Oh wait, my friend wasn't even Rudra Singh. He had a different last name. Never mind. I'm just tripping.
Yeah.
Okay, so he's like, "Keep up the good work. I'm only in middle school, but this podcast is really interesting. Hopefully I get into U of T as well." That's dope.
Yeah, that's awesome.
Okay, hopefully we inspire some people.
Yeah, it'd be great to see some young minds come to U of T to learn about what we're learning right now. He also later said, "This is a lit video on Astronomy Part 2. And he said,
I know that
you guys should do Part 3. So, this is why we're doing Part 3 right here.
Rudra Singh is because of you.
Yeah.
Thank you.
Yeah. We also have some love from India.
Yep. All my boys from India.
Yeah. He says, "You guys are doing a great job. Continue. Love from India." Definitely. Thank you for the encouragement.
I know. Seriously. I don't think a lot of people know how it feels. It feels really satisfying when you read comments saying that we're doing such a good job and stuff like this. It kind of also inspires us and motivates us to make more podcasts.
Yeah, definitely.
So thank you for this. Thank you. Thank you so much.
Yeah, and he also asked where from India you're from.
Oh, yeah. So I'm originally from Mumbai, Bombay. And then I moved to Toronto, or Richmond Hill technically, when I was 16 years old. And then I've just been living here since then. That's pretty much my life story.
All right, awesome.
Okay.
And then also Tazeen commented some nice things.
Oh, that's my mother.
Thank you very much. So, yeah. Thanks for all the comments, everybody. Make sure, if you have any questions or anything you want to say, make sure to leave a comment. We'll definitely be checking them more regularly from here on out.
And to be honest, we might even do this kind of segment before an episode if we get a bunch more comments, where we just talk about a few comments, some that really stuck with us, stuff like that.
Definitely.
And we might make it like a segment before an episode. So let's see.
Yeah.
Let's see.
All right. So Astronomy Part 3. Let's get right into it. So today, I know I said this on the very first episode of Astronomy. I said that we were going to talk about retrograde motion, which we never actually came around to talking about retrograde motion. So, some of you have probably been curious. Maybe you Googled it, already spoiled it, but I'm still going to go over it because I really enjoy it. And it brings you back in time. It brings you back to when you would see these phenomena happen before your eyes and you couldn't explain it. So what is retrograde motion? Retrograde motion is something that happens with the relative positions of planets in the sky.
Okay, important note, very important note. It's not an actual thing, it's just apparent retrograde motion. Yeah. The planet doesn't actually move backwards. Just important note before you begin.
Well, you just spoiled it.
Oh, did I spoil it?
Yeah, so
oh no, I spoiled it.
It's when we see a planet in the sky, such as Mars, and then at one point it starts going backwards on its orbit, and then turns back around and keeps going straight. So in the 1500s, they thought that the Earth was in the middle of the universe. So this made absolutely no sense, because if everything is orbiting around the Earth, then it should just follow a straight line. So when something goes forward and then backwards and then back again, it's like magic, right? It doesn't make any sense. But when what's-his-face decided to say that the Earth was in the sun was in the middle of the universe, everything changed.
That's in our solar system.
Oh, right. I wasn't even paying attention.
How do I not know who this? Wait, what?
Okay, I think it's Copernicus, right?
Oh, this is Copernicus. Yeah, of course it's Copernicus. Yeah.
So what he did was he wrote a book, and in that book he stated that the sun is the middle of the solar system, not the universe. And basically he didn't publish that book until right before he died, because he knew that the church would crucify him for it, which they ended up doing, I'm pretty sure. So he released he wrote it when he was like middle-aged, but he just kept it unpublished until the very late years of his life. So this actually explains retrograde motion, and there's a really good animation that you can find that will kind of make it super clear, that my explanation will not do justice to. But you can find this, just Google apparent retrograde motion and you'll see it. But basically, the further away you are from the sun, the slower your angular velocity is, which means your orbit takes more time. That means the planets, they're called inferior planets. So the planets that are closer to the sun than you, basically, they complete their orbit quicker. So there comes a point, right, that planet will pass you in your orbit, but it'll pass you. In your eyes, it'll pass in front of the sun and just pass you in your orbit.
So basically, because Mercury and stuff, especially Mercury, moves so fast and is so close to the sun relative to us, it just looks, again, apparently speaking, as if Mercury is moving in a retrograde motion.
No, that's completely wrong.
Is that not what?
No, that's completely wrong.
Isn't that not what you're talking about?
No.
Isn't that Mercury's apparent retrograde motion? Isn't that the whole thing? Okay, so after a quick fact check, we just found out that Mercury is in fact also in apparent retrograde. I don't think right now, but it does happen quite a few times in the year. And it also happens with Mars. So both of us were kind of talking about the same thing, just about two different planets. So we were getting a little mixed up.
Yeah, that's right. So this happens for every, it's a relative phenomena. So it doesn't matter where you are, it'll happen to some degree. But just because we're on Earth and we're in between Mars and Venus/Mercury, we see it a lot because of how close the inner planets are to the sun. And so I really do recommend you just search retrograde motion to see the animation of it. But what happens is that when a planet passes another planet from the inside orbit, the line of sight from the inside planet to the outside planet goes from one direction and then goes backwards in the sky and then backwards to the original direction.
It's really hard to explain. Try to explain visually on a podcast.
But it does like a loop in the sky. And it's impossible to explain if the Earth was static and everything was moving around it, but it's very easy to explain once you put the sun in the middle of the solar system. So yeah, that's it. At least we finally got through retrograde motion.
Finally spoke about retrograde motion.
Yeah, let me take off my hoodie real quick.
Yeah, so retrograde motion is just an important concept just in general, and especially because the Mercury retrograde was a huge thing in Einstein's time. Basically, the field equations, one of the reasons they were made was specifically, I think it was the field equations, right? I'm pretty sure they were. Specifically to calculate the apparent retrograde orbit of Mercury and the orbit of Mercury in general and why it's so weird. because the orbit of Mercury is in fact just plain and simple weird, and they couldn't really figure out why. And that's why field equations really helped and stuff like that. And also understanding about apparent retrograde motion.
That is absolutely correct.
We can talk about a concept that I think is really cool. One of the, what's the word that I'm looking for with P?
I have no clue.
Oh my, one of the postulates, one of the postulates for special relativity, isn't it? I'm pretty sure. Gravitational lensing, where light bends in a gravitational field. And because of this, actually, we are able to view a lot more things than we could have ever seen. So let me explain how this works. So basically, let's say there's a galaxy really, really, really far away and nowhere in our field of view whatsoever. Obviously, we wouldn't be able to see it, as I said, because it's not in our field of view. Now, let's put a sun or a huge star right in the middle of the galaxy and us. And remember, I'm saying this is completely hypothetical. There's nothing in between. Just a galaxy that we can't see, and us, and now this huge star in the middle. Basically, what happens with gravitational lensing is because this huge star in the middle creates this gravitational field around it, the light from the galaxy, even though not able to reach us, bends around the star, and then hypothetically could reach us. So we can actually still see the galaxy through gravitational lensing because light can bend in a gravitational field. So this is a really important concept in astronomy. So
yeah, this also happens with our own sun. We'll see, but less dramatic, of course. We can see stars that should be right behind the surface area of the sun in the sky. So the stars should be like right behind the edge of the sun, but we'll actually see them right above the edge because the light of the star coming in from very far away will just bend around the sun because of its slight effect on light and then hit the earth. But of course we won't be able to see a star that is directly behind the sun because the sun...
Would we not...
Sorry?
Wait, isn't that the point though, that we can see it if it's directly behind?
But
if it is, we'll see like multiple projections of it. That's the interesting thing about gravitational lensing as well. A lot of times, if there's one star, you might see it like 2-3 times because the light is being bent so many times around the star, around the parent star, that it comes to you like there are like 3 images, and that happens a lot with gravitational lensing.
Really?
Yeah.
I didn't know
so, yeah, it's a pretty cool effect where you see 2 of the same thing.
For our sun, it only happened like stars that were a little bit under the horizon of the sun.
But in 1990 something, they tested this postulate and it proved to be true, obviously, where I don't exactly know what they did. Again, probably should have done a little more research before stating this fact. But basically, they proved that gravitational lensing does in fact occur because at night, I believe, they saw a star or a set of galaxies or something like that that, again, wasn't in their field of view, was originally behind the star, so shouldn't be able to see it, but they still saw it due to gravitational lensing.
Yeah, and
I think that is what proved one of his postulates.
You can also see gravitational lensing with like the Hubble telescope. You can see a star, like a single star, and then around it there'll be like a halo. But it's actually just a galaxy being like splattered around the star because of gravitational lensing. And it has like this weird effect. I'll find a picture of it and I'll put it as the thumbnail of this episode.
Yeah, gravitational lensing is a pretty again, it's really hard to explain a lot of these concepts without, showing
no, I can't do that. I can't put it as a thumbnail because we already have like a established thumbnail for the astronomy episodes.
Oh yeah, that's true. That's true.
Oh well, if you have the technology to find this podcast, you have the technology.
Yeah, exactly.
Find
I'm
this
pretty
picture.
sure you can search on Google gravitational lensing images.
Okay, so talking about stars in the sky, awesome segue. This is my key phrase right here. I always say this. I say back in the day,
Oh,
All right. Back in the day
back
when
in
they
the
used
day.
to look at stars and they were really bored, this famous Greek astronomer, his name was Hipparchus, he decided to just write down for 150 stars in the sky their apparent magnitude. Well, back then it was just the regular magnitude because they didn't really understand stars all that well. So
No,
he's
but when you say apparent magnitude, you just mean basically just the brightness of the star relative to where he
yeah,
was on
I
Earth.
can explain that though.
Oh, okay.
So, it was on a scale from 1 to 6, 1 being the brightest and 6 being the dimmest, and it was a logarithmic scale. And after doing the math in modern day times, it came out to be around each order of magnitude is around 2.5 times brighter than the last.
Mm-hmm.
And yeah, this is like approximate because back then, like, he created the scale with his naked eye, but we just used that scale and expanded it to be, to reach stars such as our sun and even dimmer stars. So the scale nowadays goes all the way down to -26. And remember, the dimmer your star is, the higher your rating is. And so the brighter you are, the lower your rating. So -26.83 is for our sun. And then we have noted down stars that have a rating of 30. Which
was Vega, right? 1 is Vega, right?
I'm not sure.
I'm pretty sure 1 is Vega.
But yeah, you can just imagine if you have a rating of 30, it is 2.5 to the 30 times dimmer than a 1 rating on the scale, which I don't know if that's a relatable statement, but it is what it is.
Oh no, sorry. No.
What?
Which is the one that has of 0? No, sorry, not 1. It's 0. Which star has 0 relative oh crap, I forgot. Or was it absolute magnitude that was 0?
I don't know.
No, that doesn't make any sense.
Let me explain this first. As technology improved, we wanted to classify stars a little bit better, right? Instead of just saying, oh, you look bright, so you are this number. So what it is that apparent magnitude, or yeah, that's what it's called. Apparent magnitude is basically just how bright the star is from the Earth. But what that doesn't take into account is its intrinsic luminosity, right? Which is just how bright the star is on its own and how far it is from the Earth. So if a star is super bright relative to another star, just as a characteristic, but it's further away than the dimmer star, then they might seem like they're the same brightness from the Earth. So instead of having this weird like relative scale where like stars can appear dimmer than others, but in reality they're not, we decided to create the absolute magnitude, which is the magnitude of a star 10 parsecs away from the Earth. And I will actually, if we have time later, I will tell you exactly what a parsec is, but it's just it's a big distance.
We can just go through it really quick.
Okay, so really quickly, it's if you have a right angle triangle and one end of the triangle is one astronomical unit. The hypotenuse is it's basically 1 parsec, but basically, yeah, this is hard to explain. So the angle,
basically a parsec is 3.2 light years. That's a very simple way to just understand it. Okay. 1 parsec is 3.2 light years. 10 parsecs is 32 light years. So the absolute magnitude of every star is simply measured 32 light years away from it.
Okay, but what it actually, like, a parsec stands for parallax second, and so the angle that you're looking from is 1 arc second, which is 3,600th of a degree. Take that in. So you have a triangle with that angle, and the projected distance is a astronomical unit, and the distance of that projected astronomical unit is 1 parsec. This is so difficult to explain.
It's a little difficult to explain. I understand the difficulty you're going through, so makes sense.
Yeah, anyways.
Also, interesting fact about, because we're just talking about these magnitudes, because we're also talking about astronomy, I don't believe if we have mentioned quasars in these astronomy episodes before, but quasars are basically just black holes surrounded. It's like a black hole galaxy, kind of, but it's not an entire galaxy. So a quasar is kind of like a galaxy that is active. That means the black hole is currently feeding off of the galaxy, and there are particles being jettisoned from both sides. So if you just simply search up a picture of a quasar online, you'll immediately understand everything I'm saying. Basically a black hole with a galaxy. The things with these quasars is that they can be so bright that you don't really recognize, and that's kind of just throws off the entire magnitude scale. So interestingly enough, a star that's mere 3 light years away can be outshined by a quasar that is 30 million light years away. And there's actually a picture of this where there's a quasar and a star pretty close, and a quasar like 35 million light years away, and it's still brighter. Mm-hmm. So quasars are really cool and completely just throw off the magnitude scale.
And the reason why it's so bright is because of the friction between all of the material in the accretion disk, accretion disk.
The accretion disk is also like active. The fact that the black hole is active is what makes it the quasar.
Yeah.
And that's also what makes it crazy bright.
Mm-hmm. It's
so funny that a black hole and a galaxy, like just dust particles surrounding a black hole, can be so bright.
Yeah.
So crazy.
That's what happens when the laws of physics are in play.
So weird. Astronomy is so weird.
Yeah. So I was going to talk about intrinsic luminosity right before we got into this whole parsec discussion. So intrinsic luminosity, this takes us back to the Gauss's law days, where it's kind of like, what's it called? The flux, the electric flux. So instead of talking about like how much an electric field is penetrating a surface, we're going to be talking about how many joules per second are radiating from a star per unit area. So it's very similar to Gauss's law. It's basically the flux is equal to the luminosity over pi r squared, which is similar to what you would do for a point particle. Mm-hmm. And then when we get to absolute magnitude, basically you just take we compare it to the sun, because the sun is the easiest star to compare it to, because we can study the sun very closely and very accurately. So what you do is you compare the sun and you say, okay, well, if we have the sun at 10 parsecs away, it would have this scale, and then you take the radiant flux of a star you're trying to find out the absolute magnitude of, and then you would compare it to the radiant flux of the sun at 10, or not at 10 parsecs away. But just to conclude, the definition of absolute magnitude is just the apparent magnitude of a star at 10 parsecs away from the sun, or from the earth. That's just what it's defined as. So moving on, for the last topic of the podcast, I wanted to talk about the International Space Station. So the ISS is actually 2 football fields in length, which it doesn't look like that by when you just see pictures of it, but yeah, that's actually how big it is, and most of it is just solar panels to be able to redirect it to continue to look at the sun to get more power, so they can power the entire the insides of it.
I'm not gonna lie, I don't know an awful lot about the ISS, because if I'm not mistaken, isn't it mainly just like a revolving laboratory mainly? Because the advantage of the ISS obviously is pretty clear. The fact that it's quote unquote zero gravity situation that makes it very easy to do a lot of zero gravity experiments. And there are a lot of experiments that but that give you a different result or tell you something interesting in a zero gravity environment. So zero gravity, or microgravity technically, is a very good environment to do experiments in, and I really think it serves well. But to be honest, I don't know much more about the ISS than just that.
Do you want to explain why you said quote unquote?
Oh, yeah. Okay. So, I probably should. So, obviously, a very big misconception for spaceships and ships orbiting the Earth or orbiting any planet is that there is zero gravity, right? Like, people see images of ISS astronauts and they're like, hey, it's weightless, it's zero gravity. But that's just like entirely false. That's just nowhere near true, because there is, in fact, gravity. Gravity is still present. Just because you're 100 kilometers above the Earth's surface doesn't mean gravity doesn't exist. Like, the moon is still orbiting the Earth because of gravity, right? What makes you and your spaceship weightless? So the reason you're weightless, or apparently weightless, is because technically a full orbit is you are continuously falling to the Earth. So imagine you in, like, I don't know, just a hunk of metal falling straight towards the Earth. Just picture you falling straight towards the Earth. Obviously, you will probably float. And let's say you fall towards the Earth forever. That's basically an orbit. That's exactly the definition of an orbit.
Yeah.
So that's what's happening with the ISS. And that's why, relatively, again, that's why I said quote unquote, it's a zero gravity environment. But it's not actually zero gravity, because gravity still exists. Always does.
Yeah. So,
I think now we're over 30 minutes.
Yeah.
So we can probably just wrap this up.
All right. Yeah. So
yeah. Do you want to say anything else?
Yeah. This has been another interesting episode.
Mm-hmm.
We will be back very shortly with another episode this week.
Aren't we trying to do once a week now?
Yeah, I guess so.
Yeah.
So yeah.
Yeah. So to all those people who are watching, listening, we are updating our schedule to a little more relaxed schedule now. So instead of like a kind of more erratic 1, 2, 3 times a week all over the place, we're going to do a more stable once a week. The day hasn't been decided yet. I don't know. We might just do, Wednesday, Friday, something like that. Doesn't really matter. But once a week is basically going to be our schedule now.
All right. So make sure to leave a comment, follow on Spotify or wherever you're listening. And so this has been the Math and Physics Podcast. I am your host, Parker.
And I'm Ray, and we will see you soon.
Peace.